Good morning, everyone, and welcome to today's GoFly Master Lecture. To get us kicked off, I'll pass it over to Gwen Leiter, CEO and founder of GoFly. Gwen?
Thanks, Paul, and welcome, everyone. We have an incredibly exciting master lecture for you today. As you all know, the GoFly Prize is sponsored by Boeing. And in addition to Boeing serving as our grand sponsor, we are also joined by several international aviation and STEM organizations around the world, as well as several corporate in-kind sponsors who provide software services and products directly to our teams. Today's master lecture features Dr. Shane Arnott, who is the director of Boeing Phantom Works International, and he's also a senior technical fellow at Boeing Defense, Space and Security. As director of Boeing Phantom Works International, Dr. Arnott is responsible for Phantom Works International's presence in Australia, the United Kingdom, Korea, India, and Saudi Arabia. The Phantom Works mission is to engage customers to understand their needs and the development of the resulting prototypes of new products and systems. Dr. Arnott is a senior technical fellow with Boeing, and that means he's recognized as being within the top 0.1% of all Boeing engineers. And he's also the international spokesperson for the fellowship. Dr. Arnott has been with Boeing since 1997. He holds a Bachelor of Engineering with honors, first class, and a PhD in systems engineering. And we are so pleased today to be able to welcome Dr. Arnott from Australia, and we will learn so much from him. So without further ado, Dr. Shane Arnott, thank you so much for joining us today.
All right, well, thanks, Gwen. Let's get set up here. So just stick it in the slideshow. So good morning, good afternoon, good evening, wherever you're watching this from. As Gwen said, I'm coming here from Australia. The sun's just come up here behind me. And the task that I've got today is to give a presentation on the use of modeling and simulation as it relates to aircraft design. And it's really designed for all the GoFly applicants and for you guys to think through how to use modeling and simulation to make your design better and hopefully more successful as you go through the program. So as Gwen said, I'm from the Boeing company. We're very proud sponsors of this program and have been really impressed with how it's going. Although I'm from Boeing, this presentation does not express the views of the Boeing company. They're personal and they're put forward as for the purpose of education into this particular program. All right, so let's begin. So what I wanted to cover today is to convey some of the basics on modeling and simulation and hopefully provide some motivation as aircraft designers on why you should care about modeling and simulation. And then hopefully if I achieve that goal, then to start talking about the best way to apply modeling and simulation within the context of aircraft development. Introduce some concepts around model-based systems engineering, the system model digital twin and why that is useful in the creation of new air vehicles, and to give some specific recommendations on models that I would recommend that each of you consider as you're going through your system development in order to improve your proposals and your activities. And then hopefully we'll have some time for questions at the end there. So what is modeling and simulation? I'm sure many of you are high school, university graduates. You would have studied simulation of some degree. You would have heard words like stochastic, deterministic, all these types of things. Modeling and simulation, personally, that's my background, is a very live field. As a practitioner, there's a huge amount that you could spend a whole day sort of talking through modeling and simulation. It's a rich and growing field. It can actually be very challenging to navigate, and particularly when you're in an adjacent field or a field that just wants to apply modeling and simulation. sometimes it's not that easy to sort of leap in and go, well, okay, what makes sense to me? So what I would offer is, let's start sort of unpicking, what is modeling and simulation, and use dictionary.com to sort of help with the basics. So, and what's the difference between a model and a simulation, and does it even matter? So a model, by definition, it's typically something that's a smaller scale than the real thing. It's used as an example, to follow, to imitate. It's a description of some sort for a system of a process or a process to help you in predictions. Sort of sounds useful. And it might be a particular version or a design of a product that maybe you can leave for later and compare for the future as well. Simulation is an imitation of a process, can be the act of pretending. And for computer models, creating something for the purpose of study. So for all of this, the difference between modeling and simulation, I would say it doesn't really matter. It's all the same thing. Modeling and simulation together is a tool to help you think. And this is an important concept to come at it from this angle, that if this, as a tool to help you think about your design, or to help others think about your design, perhaps people you need to influence, say customers, then it's not coming at the right angle. So always have that in mind, that this is here to help with something else that you're doing. And typically it's helping you think in order to get further down track on whatever that other thing you're doing, which in this instance is designing an aircraft. So modeling and sim is there to help you think. So a couple of terms to help your gauging of your thinking, which I'll sort of throw out there, is one of the dimensions that you can measure modeling and simulation is by virtue of how inclusive of humans it is. So these terms of live, virtual, and constructive get thrown around a bit. So the definitions: live is real people operating real systems with pieces that are simulated, typically dangerous pieces that are taken out, like the picture there where there's real people in the field, but the weapon effects will be taken out and simulated in order to enable experience of that particular domain of infantry or land warfare without the dangerous pieces of bullets sort of flying around. So that's an example of a live simulation. Virtual is real people, but operating simulated systems. So like the picture that's depicted there. So trainers are typically like this, where you've got a real human, but they're in a representative environment of the cockpit or the user interface, whatever that may be, of the particular system in order to experience or train in that particular space. Sometimes that's called human or operator in the loop simulation as well. And then the last one, constructive, is simulated people or systems operating simulated systems. So full closed loop, if you will, artificial intelligence driven simulation. So sims typically tend not to sort of fit neatly into any one of these categories. It is a continuum, but it is something to sort of frame the where to peg a particular simulation by how much involvement humans need to have as part of it. And that sort of helps you with the design, or at least the selection. On the right-hand side, probably one of the most important terms or concepts is V&V, or validation and verification. So simulation is useless unless it's got some sort of application. And that process is called verification validation, or V&V. And the way simply that it's broken down is in the light blue bubble, you have the real world. So the real world that's been created by whatever you believe, which is the system we live in, and all the great stuff happens in. You then have a conceptual model, which is an algorithm that represents something in the real world. So force equals mass times acceleration, for instance, is a conceptual model. So it's an algorithm of some description. And you need to validate that that's a good thing. So typically there's papers out there that do that sort of stuff. Then the model, which is the red box, if you will, that's the simulation or the model that you create, the computer code. You need to go through the process of validation, which is ensuring that the model is sufficiently accurate of representing the real world system. So your as expected or as modeled maps to the as observed in the real world. And then verification is going back with the model, making sure that it's implemented properly back against the conceptual model. So these steps of validation and verification are very important when you're creating a sim, that you're going back and you're relating that back to the textbooks that say, hey, this is how said system works, whatever it is, the algorithm, that you're implementing it correctly, and then also that it represents the real world adequately enough for the purpose that you're performing or you're applying the simulation for. So, you know, who's got time for modeling and simulation? You know, you guys are too busy making the world's best aircraft, like the picture there of the battleship aircraft. You know, you just want to get out there, plug systems together on the bench, then stick wings on it and see what happens next, right? And you iterate that enough, you're going to get there at the end. And I hear this a lot from aircraft designers. I'm too busy for that stuff, and plus it's going to slow me down. You know, we've only got a limited amount of time, and I just need to get into it, right? So, and you know, we've got all these great tools. So stuff like Dan Raymer's book, which is a fantastic book. If you don't have it, go out and buy it. This is the Bible as it relates to designing aircraft used throughout the industry, and Dan's an awesome guy. And then we've got tools like the Systems Engineering V. You know, we've been using this thing for forever. And it's a great process. You know, you start at the top of the V, your concepts come in the top with your requirements, you devolve your requirements into systems requirements, subsystem, detailed design. So it goes through a nice process, and then you come back up the other side, make sure your design's implemented properly, and good things happen out the back end. And as you're going through that process, you're able to backdrive your verification and validation from your as designed to your as built. You know, everything's fine, right? Well, one of the reports that are out there that's always quite depressing is a group called the Standish Group, and these guys track engineering projects writ large, so not just aerospace programs, but I'll get to that. And generally, as engineers, we're doing a terrible job actually bringing stuff to life. So by their industry-wide activities that they do, less than 30% of engineering programs are a success, which means they'll deliver on time and within the scope, the original scope. Over half are delivered in the challenge category, which means that they're late or their scope's been reduced. And nearly as many fail, never get delivered, as are successful. Success and failure factors are fairly common across all of these programs. User involvement, having the user involved enough early, which is something for you guys to think about, not to innovate in a silo. Clear statement of requirements. I'll come back to that. There's a theory there. Scope creep that happens as a result of that, and realistic expectations. You know, clear statement of requirements is an interesting one. Engineering programs tend to be long programs, and customers change their minds over the period of time. And there isn't a great way in this process to handle those changes. You know, you really want your changes locked in early, or your definition locked in early rather, because you need to go through that decomposition sort of phase. And if anyone changes, then you've got to go back up to the V. So it doesn't sort of work so well. Now, just to depress you further, aerospace development is probably the worst out of all the engineering disciplines. And this is a busy chart, so let me brief this left to right. So DARPA did a great series of studies in the last sort of 5 years or so. And let me explain the chart. So the chart on the left is the design time, basically the process you guys are going through to create a new system on the left-hand side. And that's measured in months. Across the bottom is complexity, fairly crude measure of part count, source lines of code. it's just indicative to sort of talk about how systems are getting more complex over time. The light green bar that sits across the bottom, that's the integrated circuit community. So these are the guys building CPUs, those types of things. They're actually doing a pretty good job. So year on year, or every 20 or so months, they're pumping out a new generation of processors that are increasingly exponentially more complex and capable, and they're pumping it out the same timeline and pretty much for the same cost. Schedule and cost are fairly tightly integrated. Then in the auto industry, they're actually in a really nice sort of downward trajectory there, from cars taking, of the order of 60 months down to, of the order of 18 months today, although Elon Musk with Tesla is starting to bring things back up. But generally as an industry, the trend's really nice. Aerospace, it's not in a good place. So from the Century series aircraft, and these are all military programs, up to, more recent programs like the F-35, F-22, with a few exceptions like the Boeing Super Hornet, I'll say. But for the most part, we're on a really bad trajectory as it relates to design time, creation time, if you will, of new aircraft. The inset in about the middle of the chart there is a little bit of a different axis where it's unit cost for aircraft, which I said is, roughly or loosely correlated with your design time because you need to recover your cost. And the projection of DARPA is that in about the 2050, 2060 timeframe, the whole United States Department of Defense budget will be able to afford one aircraft. One aircraft if we keep on this path. And that one aircraft will get shared between Air Force, Navy, and Army, different days of the week. So we need to do something different to change things. So why are things sort of going crazy? Well, our systems are becoming much more complex, and that's sort of driving the complexity piece down the bottom. Software is a big part of that, and that cyber physical sort of crossover and that being difficult. Connected systems is a big one. So as we create systems, and certainly for you guys, this will probably be a big part, at least in the future, of your systems, that they need to be connected with different other systems, and that explodes your interface dimensions as you're designing. And on top of that, we want the aircraft to do something interesting. So typically we're putting payloads onto the aircraft that are super complex themselves, as complex as whole aircraft sometimes. And you're getting this system of systems effect that's causing this explosion. So the graphic to the bottom right is also from that presentation, which is, in theory, you're supposed to be going down the V, things should decompose in a certain way, you get to optimize at each level and everything's happy. But the realization is on the right is you have this explosion of complexity, and then also a couple of weak links between certain levels that make fragile and complex architectures. So the bottom line is aerospace engineering is trending in the wrong direction, and as a community we need to do something different. And with all of you guys who are new entrants into this space, this new golden age, as our Chief Technology Officer, Dr. Heislip, talks about, it's important that you guys start thinking differently and coming into this new age. So what we propose, and something that's been kicked around a little bit, is this concept of model-based systems engineering. So the V doesn't change, and we don't want to change the V. The V's there, and it's very important as it relates to safety, and a bunch of documents that you need to get to certification. So a whole heap of lessons learned are in that V. So you still do your design up through your physical, all that sort of stuff. Nothing changes from the old school. But I guess what we're introducing is the concept of the diamond. And while the bottom of the V is for physical systems, the top of the V is for the digital twin, or the model. And as you're going through your design, you're actually creating your model. As you're creating your physical system, you're creating your virtual physical system at the same time. Now, in reality, the orange piece, the top of the V, correction, top of the diamond actually is a little bit ahead of the bottom as you sort of go through. But what that enables you to do is to have this approach where you're using models you don't have to wait until you're coming up the back side of the V. You're actually using your models as you're coming up the top of the diamond to be doing that validation exercise early in the life cycle. And this is where things go wrong in your design sort of phase. So instead of just having that back driving effect of your verification validation sort of happening as you're coming back up and building, you've actually got a model that you're creating, a digital twin, as you're going along, and you're able to sort of go, is my design working? You know, are my technical performance measures right? All these types of things. And as you progress, you're then creating this model and creating this digital thread, if you will, to help not just with the platform that you're building, but eventually your production system, which I'll touch on, which leads into your service and support. It'll help with your test and evaluation hugely as well, if you've got some great models across all of this, and certification and those sorts of things. So this is an important concept to bring to bear, that you basically have this whole other track along with your V that we all sort of follow, know and love, but there's a model component to that, which is just as important, but there to reinforce the activity of creating a product at the back end. All right, so hopefully I've convinced you that using modeling and simulation is important, and particularly in aerospace, because we really need to change the game. So, okay, Shane, so what should I use? You know, what are the 5 software products or tools I need to go get? Well, the old adage of all models are wrong, some are useful, totally true. So simulation does not equal reality, and that's never going to happen, or not in our time. So the oasis, the matrix, doesn't exist yet. It'll be cool when it does, but not yet. So what I say is world simulator isn't yet to be invented. Matrix doesn't exist. Seek fitness for purpose. So back to the tool, help you think. What's helping me think to get towards my aircraft design? It's an important sort of frame to come at. The next piece is people sort of offer that modeling is part science and part art, which is a particularly unuseful statement because it doesn't really help you sort of know which tools to pick to apply it. What I will say is the art is in good project management. It's pretty simple. So given that you're following your project management principles, which you all should be, you will know when you're building your schedule which bits are a bit squidgy. So you would have laid out your schedule and you're like, I'm not sure whether this is going to be 10 days or 10 weeks. I'm not sure. So there's some risk associated with that part of your schedule. That should be reflected in your risk management, your risks and opportunities queue. So anything that's in that yellow or red area, you should be worried about that. Simulation can help you burn down that early. So with each of those areas, be guided by those, and anything that's sort of in a likelihood space that's not good, so the yellows and the reds, be thinking about, okay, with the top of the diamond, how should I be directing some tools and activities against burning that likelihood down? And through understanding, it may go up, may come down, but usually you'll get a better handle on it. Sometimes consequence moves as a result because you learn more, but typically not. It's more your likelihood coming up and down. And then the other big one is technical performance measures. So this is another thing you should be doing, good project management practice. So with each of the key criteria, both high-level requirements and also derived ones that you may create, you should be creating, let's say for weight, for noise, which is one of the GoFly criteria, that you'll have a hard line, if you will, your red sort of line there on the chart, where I cannot exceed this number because GoFly says I can't. And then where you want to be, your blue line, so your objective capability that you want to hit. And then as you're going through to sort of track those. For each of your TPMs, that'll help you know what your fidelity should be or your resolution of your modeling as you sort of go through and create these sort of tools, because you want to be able to be predicting your TPMs. sort of early, and then as you're learning through the cycle, be able to go backwards and forwards. So nothing replaces good project management. Modeling and simulation becomes a really powerful tool coupled with that to help you with knowing which tools and to what fidelity you need to select those and apply them. All right, so now to some recommendations on what are the tools to apply in this particular space. So the first one I'll say in the creation of your digital twin is a concepts trades model. So something that as you're starting to come up the V at the very early stages, something that's a system performance model. So something that represents the effect of your system. And it's good to frame it from a customer standpoint. So customer value centric. And the attributes of these sorts of models tend to be highly virtual, so people can come in and experience it, a bit like the graphic or the video that you're seeing in the bottom right that's hopefully coming through. Pieces are constructive, but it enables you to have that visual experience as part of the activity. And you can couple that with virtual reality, like the headsets you're seeing there, representative control, sticks and throttle, etc., force feedback, joysticks that are out there that are cheap, for instance. And you can also potentially buy off some of the requirements, like the visibility sort of requirement, for instance. Use this sort of level where you've got the expectation, or the effects, I should say, basis of each of the approaches. And let's say within your team, there may be a little bit of conversation on which way is the best approach as well. So, you know, the course notional diagram in the top right is comparing 3 different approaches. Let's say you might be looking at a jet-based approach, a rotor-based approach, a tilt rotor, and you want to have a look at the high-level criteria of the what-ifs. You know, what if we were jet? What's the so what as it relates to noise? What if we were rotorcraft? What's the so what as it relates to endurance? That type of thing. So they're the knowledge gaps that you want to be looking to close as part of that early phase. The what ifs, major system trades, left and right. And then also, is this useful? You know, at the end of the day, you want to sell this to someone. You don't want it just to be a museum piece. So having something where you can work with potential customers or investors, for that matter. Building aircraft's really expensive. So you probably want to be engaging with folks and just sort of say, you know, is this about sort of what you'd like? You know, is this useful to you? Concept trades, experience the effect of the system, demonstrate to customers, gain feedback sort of early on. So I would recommend that you create a concepts trade model. Use some of these game engines that are out there. There's plenty. This particular one is Bohemia. There's X-Plane, there's all sorts for you to sort of have a look at and leverage. That can do that effects level modeling very easy. So now we're getting into the real value add. So the digital twin and the systems development model. This is perhaps the more useful sort of one. So as you're going through and you're creating the design for your system, and as the graphic on the right at the top, you'll be creating block diagrams. And this is completely notional. But something similar to this, you're having inputs coming in, they're going in through some processing boxes that then get fed into a flight management system of some description that then translate out into flight control mechanisms like actuators that then go out to physical control surfaces. Similar thing, mission computers, non-flight things, but say displays that are coming up to operators of your system, you know, weather, air traffic control, you know, where is everyone else who's out there, data loggers, those types of things. So as you go through with your block diagram, start thinking about how to be creating simulated versions of each of those blocks. And when you're building the digital twin, which is the graphic to the bottom, have a think about your framework such that you're not just doing simple stimulation, dumb stimulation type modeling. Start creating a full digital twin environment, which means you need concepts And there's a bunch of toolkits that are out there, but have concepts like movers or the dynamics, you know, rotor, jet, tilt rotor, sensors, GPS, radars, that sort of thing, processors, anything that you're doing plus humans are sort of processors, communications, devices, that sort of thing. And also services for the simulation, if you will. So scenario database management, geospatial, being able to read in maps, that sort of thing. Interfaces to industry standard simulation formats like DIS or HLA, that sort of thing. And quite often these are constructive. So what you're looking to do is sort of take pieces, or what I would suggest is from that digital twin as you're creating it, and sort of represent pieces. So some of your processors, mission computer, your sensors are the inputs coming into your nav system, that sort of thing. Your movers are stimulating your air data system as you go. So you're really looking at representing that subsystem behavior, the performance expectation early to set your TPMs, primarily constructive, subsystem focus, and you're thinking about the interfaces. So early on, you're starting to look at logically, does my design make sense? Logic, do I have the logic where I'm passing the information from each of the major pieces of my design that it works? You know, is it a complete design? Do you find out that actually I need a GPS signal coming into my mission computer? I haven't got that. So you have to go back, you update your design, you put an extra splitter, and you've learned that because you've gone through the logical steps because of the simulation environment. Tool to help you think. Phase 2 of this is probably where the real value comes in. So as you've got all your simulated pieces of your block diagram, if you will, you then transition to your bench test or your iron bird, let's say. So as you're starting to select your real systems, so they're starting to replace your design elements and your simulation, you're now blending into from the constructive environment to the live environment. You're starting to go from the as expected modeled sort of behavior to as observed, because you've got the real systems. You can then start using your digital twin to push a little bit further out from your architecture, and it becomes a stimulation environment from being simulation. But you can plug and play. You should be able to plug and play that some elements, you may just have a problem just with your flight computer. So you just want to be stimulating at the edge of the flight computer. But as you get more and more complete, you'll push that further and further to the edge. So the attributes then are that blending of live being the real hardware in the loop with the constructive behavior models of the select elements. The interface stimulation, which I sort of talked about. So talking the real stimulation. And you're starting to get that feel for, are all my subsystems working together with the stimulation that's going in? And then as you're coming over the top of your V of the diamond, rather, you're getting your as expected from the previous iteration of the model to the evolved one where you're getting the as observed. When you get the as observed, backdrive that into your model as well, because you're going to need that back and forth to get your V and V that I talked about. Now, once you've got all of this, a really useful thing to go and do is go and do some really crazy stuff with it. Go do things that are off nominal and see what happens. Because in flight, things happen that you would not expect. And if you've got that ability with the digital twin model, you can take your system into regimes that you've never expected and then just test. And all of a sudden you'll find things will start falling over. And you're able to then capture that, find your corner cases through using simulation. And, you know, someone going back and just taking the controls, doing a barrel roll. And all of a sudden you find half your flight computer logic zeroes out for some reason, which is a bad thing. So you're able to find those corner cases and architect for that in advance. Incredibly useful to have this sort of capability sort of as you go through. So this systems model, simulated first, starting to evolve into the live hardware and being able to mix and match and being rich enough that it's not just little stubs that you're using to stimulate the interface, but it is a digital twin model that you're using components as it makes sense for you to plug into your design and help you evolve that. And then also, you know, it's not to discount, and certainly important, there's a bunch of great tools out there. So this is very systems related, but from a flight standpoint, so CFD, your stress modeling, there's a lot of very well established tools out there that do this sort of thing. This is important for your flight. But as you do them, what happens sometimes is the work gets done, you maybe do some wind tunnel testing, you'll compare those two, but you put it in a folder and stick it off to the side. Take that dynamics and bank that down into your systems model as well. So all of this, you know, great work that gets done and, you know, through the traditional path will be a validation point. Make sure you're banking that value down into the model such that you're getting a richer and richer flight model, for instance, from those particular traditional modeling techniques like CFD, etc. Then the last one, which people don't think a lot about, is the factory. So at the end of the day, and as a company that sort of works for as someone who works for a big airframer, when we're building our new aircraft, a lot of the time we will be building the factory or designing the factory at the same time as the aircraft, because you can't have something that's, you know, impossible to build. You can't take it to market. So while it's not a massive consideration for you guys, I will say this is really useful, at least for you to think about as you're going through and you're doing your fabrication, your assembly, and your production manufacture. How long is it taking to get certain bits? Do you need a very special person to do certain stuff? And just to start recording that and perhaps even modeling some of it. So there's a lot of tools out there that do process flow modeling. AnyLogic, ProModel, I think Total Sim, which is one of the sponsors, similar to that, where you can start banking in, you know, what does that look like in order to punch out a product on the back end. But as you're going through and creating, start thinking about recording those steps, which will be important, because after you demonstrate whatever it is that you guys come up with, and, you know, company X who runs a big rideshare company or whoever comes up and says, hey, I want 100 of those or 1,000, you want to know what it's going to take to go from your good idea to something that you can produce. You know, it doesn't have to be production ready, but you've got enough knowledge on what it's going to take to turn the hand-built Rolls Royce that you built into something that you can pump out like a Model T Ford. And that'll help you gauge your costs for the first unit and that type of thing, because it's all time and money. That's what it comes down to, which will be your unit cost, and then also maintenance and repair and all those types of things. So just think about this one. It's oft forgotten, but a very important part of aircraft development, and it'll help you get fit for your go-to-market. So the way it all sort of comes together, you know, as I said, be driven by your project management. Nothing replaces having good project management discipline. Know your schedule, know where your soft points are, know your TPMs, know your risks and opportunities. That'll guide you in what you need to be addressing with your systems models, etc., to reduce that risk. As you come across the top, and I'm just depicting the models here that I've recommended to you guys. Obviously, the interesting stuff on the bottom of building real aircraft all exists, but start with that concepts trade environment. Have a nice, rich sort of space as well to engage with people you want to get some money out of, either eventually or through your development cycle. Having that nice visual environment goes a long way. But then when you get to the hardcore engineering, create that digital model, initially from a sim standpoint, representing your block diagram from a logical standpoint, making sure the flow works, making sure your logic makes sense. Then, as you start selecting real systems, real products, you're getting your flight dynamics. and your envelope and all those types of things. Start replacing your simulated components with the real components. And you rinse and repeat that throughout. And then don't forget about the back end. This is about building real things that you can give to real people that are safe and you can make lots of money. People often forget about that piece of it. So the whole idea is to reduce risk, increase your success, and get a picture of your air vehicle there where the post-it note is. So it's all about active uncertainty management. And that's what the top part of the diamond's all about. So to try and push back those problems that the Standish Group talk about, that DARPA talk about, trying to get out in front of those problems that happen quite early, to deal with learning that happens early as well, people changing their minds. And that's okay, having the modeling environment to enable that changing, because the cost of changing is better early than it is later once you start bending metal and cutting code. So a couple of advanced techniques which I'll touch on, but good things to think about. Use of models in your regression testing, so at your unit, subsystem and system level tests. Having models there to sort of bank in as part of your testing is a really good idea. Some advanced versions of that is actually using AI to represent your system behavior. And then in the trade space, which can be, explosive, like the DARPA diagram of the complexity, there's some advanced techniques using machine learning and other things, and concepts like the AI gym to explore that trade space smartly. So not just do a brute force approach, but what are areas that actually make sense, and that can be really useful. But the big thing that is desirable is getting to model-based certification. Certification is always the most expensive part of an aircraft. Now, I'm not saying that we're here with that, but certainly there is examples of buying down some of that certification through models. And particularly in the extreme, dangerous, difficult to reproduce or replicate regimes, SIM is probably the only way to do that. But that's only made possible by having a good documented approach to your V&V. So in your verification and validation, you want to be showing that you're doing that in a way that a third party can have a look at what you've done and understand your method and understand the results, understand you as expected and you as observed. And that your model is trustworthy, that's V&V, verified. But one of the things that you want to do there is work early with the safety authorities to get them to buy into your approach. And if you do that, then that holy grail of the certification comes a long way. So modeling and sim coupled with these advanced techniques are even more powerful and useful and can reduce your product development life cycle. So I guess in summary, as we come up to the end here, aerospace development, we're not a great trajectory that we're on from time to build these things. It's a new golden age. You guys are all part of it. Think differently. We need to think differently. So as part of that reboot, model-based systems engineering is part of that. So we offer that out as the diamond. So stop thinking V, start thinking diamond, as a way to start reducing that, and modeling and simulations obviously a key part of that. But noting that all models are wrong, some are useful. So with that mantra, get that tattooed somewhere, put it up on the wall. Use project management principles to guide your application. So always start with that, know where your holes are, develop that sense for fit for purpose. So that is a little bit of art, but that's going to guide you on where your fidelity and your resolution needs to be, like how detailed in a particular area versus another. It's not about having the world's best simulator, it's about having the world's best airplane. But to help you with that, there's a whole heap of commercial off-the-shelf tools, there's open source solutions, there's a whole heap. None of them are complete. Expect to extend and customize them. Have someone on your team who knows software, who knows enough about simulation, who knows enough about physics, and connected systems, etc., in order to model all of that stuff. Create that digital twin, evolve it over time, record you as expected through using modeling or expert approaches and and sheets, spec sheets from your suppliers, but develop that as expected. And then as you have the as observed, tune your models to reflect, do that V and V, rinse and repeat, create the trust in that digital twin. Build your first 100 in simulation. That's something that our CTO talks about a lot. So whatever it is, build the first 100 of them and test it out. But use configuration control just like you would anything else. So as you're iterating up that digital twin, you've got all those different versions or models of your evolution, such that you can refer back to it as you're doing your regression. Explore that off nominal, as I talked about, understand the limits, find out where your system breaks, aim to break your system, and then adapt the system to accommodate. Take it outside even what you expect, because that will happen. And it's not just for the platform, it's for factory, it's for training, it's for a whole heap down track. So it's really going to help you. But that said, nothing replaces real T&E, test and evaluation. It's not going to replace going out in the field, doing the real thing. But it should, and it will reduce surprises. You shouldn't be doing anything out in the field that you haven't done in the sim first. And that's, again, this mantra of as expected versus as observed, and being able to bring that together. But at the end of the day, the focus is building a product. It's all about the air vehicle. Everything is about the air vehicle that you're building. Simulation is just a tool to help you think. That's all it is. But it will help you understand your problems earlier, explore a wider space than you would any other way, and get to a great product faster. Something that you can sell to me and many others. All right, so that's my presentation. So I think we'll go to questions.
Yep, absolutely. Get to questions here in just a second. We've got a number coming in. So if you'd like to add any more, go ahead and add those into the Q&A box. So to start with, so when you were talking about the digital twin V, how much does the digital twin V precede the physical system V? You mentioned a slight offset there. So what's the right offset?
Yeah, enough. Yeah, look, it's an interesting one. I think as you're going through your design, quite often you're challenged with we're not sure. We're not sure this is the right number, particularly with derived requirements. So you want to make sure you've got that model evolved enough that you're able to do that vertical validation, if you will. Particularly when you've got a lot of elements, humans don't do that well with too many variables, and particularly second and third order effects. Simulation doesn't care. So you want to be ready as you're going through that design, and particularly your evolved or your derived requirements, that you're able to go from that first level to the second level with some level of confidence through doing some prediction to tell you that, hey, I'm okay, or no, this looks really knife edge. I need to delve deeper into this, or maybe change my design to get a bit more margin in the design because we're way too close to the edge of whatever that is. So I'm not sure that's useful, but that's basically the guidance.
Got it. And then referring back to the diamond picture, you talked a lot about adding the digital twin as a companion to the physical prototyping that's happening in the bottom of the V. But are there circumstances where the digital twin lives on its own and it's not actually a twin but leading for a period of time before you add in the bottom V again?
Say that again. Sorry.
Sure. So is there an opportunity here for people to use just the top of the diamond for a period of time and think just in the digital before moving to the physical?
Yeah, sure. And I think that was sort of the point, that you can stretch out as far as you want on the virtual front before you start doing the physical. And that's sort of part of it. So you can move a lot faster in the sim space than you can in the real world. And that's sort of the point. So you can get out in front of it and go as fast as you want to go. But there's no point getting too far ahead, because then you're off in la la land. You're grounded in whatever the real decomposition is, the real systems that you're selecting. Quite often the options that you have aren't as great as you'd expect, from the avionics providers or whatever. So you got to live within those bounds, and you want to be modeling within that. There's all sorts of stuff you can do in X-plane that looks really cool. But this is about building that particular aircraft, and you want to be doing the trades that actually matter and add value.
Great. And then people think about the benefits of using off-the-shelf parts for prototyping purposes, but is there a benefit for using off-the-shelf parts for digital simulations as well?
Yeah, absolutely. So that's what I was recommending. There's a lot of commercial off-the-shelf tools. Utilize those, but as I said, you're going to need to customize them. There's no complete design support tool out there, with the exception of there's some niche tools like your CFD and that sort of thing that are pretty much ready to go. But as a digital twin, there's no digital twin off the shelf sort of tool. And that'll change again depending on the complexity of the design, how deep you need to go, and it only needs to be fit for purpose for what you're doing. It doesn't have to be the world's best simulator.
Great, thanks. And then for some of the competitors or innovators that don't have your great industry experience, could you talk a little bit about how the diamond interacts with each other in a corporation in terms of working with prototyping group?
Sorry, Dan, can you say again? I just lost you there.
Sure. So coming from your great industry background, could you talk a little bit about how these teams interact in a large corporation? So the digital group and the physical prototyping groups.
Yeah, great question. So they're more and more interlinked. I wouldn't say that they're sort of separate. In some of my team's programs, they're the same guys. So they'll be running alongside each other. The systems engineering integration team, for instance, will be asking questions, and they're literally sitting next to them, creating that modeled sort of version that's feeding back into the requirements, or updating the design. So you sort of have that, your design team, they become very, very close with each other because it's a question and answer machine. That's what it is. It's a tool to help them think. For the stuff that, these are people with decades of experience, and it's hard. It's hard every time. Building aircraft is hard. That's the reason why the curve's like this. It's the hardest thing there is. Aerospace is the pinnacle of engineering and human achievement, in my opinion. So having different ways to sort of go through that thought process, so you don't have to wait until you're on the ramp and you're like, yeah, man, I didn't think about that in advance, or that doesn't work. And that's what happens, right? You get into that back end of the V, and there's all these surprises that occur, and that's what drives the schedule blowouts, the cost increases, the projects never making it to reality.
Great. And then related, do you have a good benchmark for what people should consider as a ratio of effort between developing virtual and physical systems?
Yeah, it's a good question. And that's certainly something we're looking to instrument as part of Boeing. The diamonds are reasonably new concepts, but certainly it's getting applied on the 797 program. A lot of the military programs have been applying it, like TX and others. So yeah, I don't think I've got a good answer for that. The focus is still building the airplane. That's the hard bit. But it's not a part-time job either, sort of running the top of the V. And it's more a conscious effort in your process and how you're sort of changing it, that everyone's charging, not just down and up the V, but across the diamond as well. And as you're observing stuff, it's driving back, you're creating that digital thread. it's as much a process and mindset change as it is, having another group that runs alongside.
Great. And then in terms of GoFly teams putting together team members to help with their developments, do you have any recommendations for building out the capacity to do the sort of digital work along with the physical? Is that something that teams should be looking for resources to help out with, something that they should consider learning along the way? Do you have any recommendations there?
Yeah, I mean, simulation's a specialization of software quite often. So make sure you got some good software folks and couple them with some really good physics and systems people. So, it's not often that you got good software guys who really understand algorithms all that well. So the conceptual model versus the model, going back to the V and V. So you want to sort of couple those folks together, really good systems guys who understand the real world with some software people, make sure they talk. You're going through that V and V exercise to force them to talk to each other and that it's representative. So you need a blend of both. You're likely to have some of those systems people anyway. You may not necessarily have some good simulation software folks. So yeah, try and find those guys. Do they have to be simulation experts? It helps, but if they're good software, they'll be able to figure it out.
Great. And then you mentioned Dan Raymar's book as being the Bible in conceptual aircraft design. Do you also have a suggestion for an M&S book for aircraft?
No, I don't. I wish there was. It gets touched on. I definitely think there's opportunity there to get something to help those lessons learned. So, look, maybe when I retire, I'll get to that.
Great. And then along the same lines, do you have any particular recommendations for real life tools that are commonly used or anything you particularly recommend? Yeah,
look, there's a lot out there. X-Plane gets used a lot, and we'll use that because it's got a great 6DOF model for the aero piece, but not necessarily, it doesn't really do systems very well. So other sim tools like I showed some screenshots of VT Mark. Mac is a company that sort of has a simulation framework that's very similar to the diagram that I showed that has all the concepts of systems and how they relate. Even ArduPilot and things like that have a reasonable simulator to help you tune your autopilot and things like that. So again, it just depends sort of what your where your holes are from your project management to, is it all aero problems? Well, go find an aero model. Is it systems integration problems, which is where a lot of the problems occur? Then go and find a framework or create a framework that you can sort of plug in those pieces. With the flow modeling tools, there's a ton of tools out there that do the factory type stuff. There's models like MATLAB and Simulink, that type of thing that can also help if you're just looking at lower level component type things and control loops. So that's the problem. The answer is it depends.
Great. And then as we come to time here, do you have any parting words of advice for GoFly competitors? Anything you can wrap up in a sentence or two as what you think is most important?
Okay. Yeah, I think take to heart the digital twin idea. Think about bringing that to be part of your development approach. And use it to help yourself think, but use it to help you engage with customers as well, both at the back end and the front end, because that's the idea, right? And simulation can be really useful to help you have those conversations outside of the actual sort of flight test. And that's the idea, right? You want to sell this thing. You want to make a lot of money. You want to be famous. So, use the tools that help you get there faster, and this is one of them.
Great. Thanks so much. And to close us off, I'm just going to pass it back over to Gwen for a couple of parting words.
Well, thank you, Paul, and a special thank you to you, Dr. Shane Arnott. Your talk was illuminating, and I know that our GoFly innovators from all around the world will take to heart your words of wisdom. So thank you very much. We encourage all of our innovators to stay tuned to the master lectures. We will be bringing you more of them as phase 2 begins, and we look forward to announcing our 10 Phase 1 prize winners on June 14th. So thank you all, and once again, a very special thank you to Dr. Shane Arnott for his wonderful master lecture. Thank you.